Hi, let us talk about the elastic constant and the work that is done by an elastic material when it's either compressed or stretched by a force that is applied to it, and also the energy that is possessed by this material. Now, this energy is what we call the elastic potential energy of the material. This is the energy possessed by an object as a result of the deformation by an external force. Now, this potential energy is similar to the gravitational potential energy of an object that is placed at some distance from the Earth. So just like gravitational potential, the elastic potential energy is the energy the object will use to return to its original length when the load is removed. So let us try to derive the formula for work done and elastic potential energy. So the question we have is, assuming we have a rubber cord, and then we tie it to a support and leave the other end of the cord, as you can see. First, we'll measure the length of this rubber and we'll tag it L. Then we'll hang a stone at this end and take the mass of the stone to be M. Now this stone will apply a force labeled F that is equal to the weight of the stone and will cause the rubber to increase in length and decrease in area. Let us record this increase in length as E and the decrease in area as A. So, how do we relate these two things? First of all, let us relate two properties of an elastic material. We have previously learned that Young's modulus and the stiffness constant or force constant are properties that we can use to describe an elastic material. So let's relate these two properties first, then we'll go into potential energy. We learned that Young's modulus Y is equal to F times L over AE. Now, if we made F the subject of the formula, that will give us F is equal to Y times AE over L. Now remember, all these things, F is equal to the force applied, L is the original length, E is the elongation, or also known as the increase in length, A is the area, and of course Y is Young's modulus. Also recall that from Hooke's law, we had the force F is also equal to KE. So since we have two equations for F, let us relate them to each other. So we have KE is equal to YAE over L. We have E on both sides, so those two will cancel out, which gives us K, which is the force constant, is equal to Young's modulus times area divided by L. And what this is an equation that relates these two properties. So if you have the Young's modulus, you can find the stiffness constant, or the other way around. So now, let's go back to work done and potential energy in a spring. Go to a fresh page. Now, we know that work done when changing elastic potential energy to kinetic potential energy usually happens when a force is applied over a distance, so that the elastic potential energy in the spring is changed to kinetic energy. So we know that work done is equal to force applied over a distance. Okay, but we started with an initial force when the spring was not elongated, and a final force where the spring was fully elongated and came to rest. So the average force that's applied when this work is done will be equal to the initial force plus the final force divided by 2. The initial force, we know, was 0 because the spring hadn't elongated. So the average force here will be equal to 0 plus the final force F over 2. Now we put that back in our work done formula. So work done, WD, is equal to 1 over 2F times the distance, which is the elongation, which is E. So our work done is 1 over 2F E. Now remember that F is also equal to KE from Hooke's law. So we can use that to find the potential energy in the spring by putting this equation back into the work done. So we have done is equal to 1 over 2 KE times E, which gives us work done is also equal to 1 over 2 KE squared. And we know that work done is always in joules. So why don't you try and see if you can derive the same equations at home for work done, potential energy in the spring, and also for the relation between stiffness constant and Young's modulus. See you in another lesson. Bye for now.